Hi everyone, in this video we're going to talk about solving basic trig equations. So by the end of this video you should be able to solve the basic trig equations. What steps do we need to solve these trig equations? Well, we're going to use algebra techniques to isolate the trig function. The most important part is to isolate the trig function. Get the trig function by itself. So to do that, we're going to add, subtract, multiply, and divide both sides by numbers, not by trig functions. We never want to multiply or divide by a trig function at all. Adding and subtracting are okay. We're not going to need that today. You will need that in the next lesson. And then if we need to, we'll take the square root. The only time you need to take the square root is when you have it squared and the trig function is completely by itself. After we do the algebra part, then we're going to use the unit circle to identify the angles that satisfy the equation. Oftentimes there are many angles that are solutions, so we do need to make sure that we list all possible solutions. And then we always have to double check our domain restriction to make sure our domain or our answers, our angles fall within that domain. So example number 1, we're going to solve 2 sine x equals 1 for all angles on the interval 0 to 360. So this right here is our domain restriction. We need to make sure that every answer we have falls between those, which is what we're used to listing anyways. So I have 2 sine x equals 1. If I want to solve for sine to get the trig function by itself, I'm going to divide both sides by 2. When I do that, I get sine x equals 1/2. If I want to identify the angles in which sine would give me 1/2, I have to understand that sine is only positive in quadrants 1 and quadrants 2. So sine is only positive in quadrants 1 and quadrants 2. That's not 2, that's 3. There we go. So what angles would give me 1/2 for sine? If you're using the hand trick, what you can do is you try to make 1/2 with your hand, which means you want one finger left on bottom. When I do that, that would give me 30 degrees. The reason we are answering this in degrees is because our domain restriction is in degrees. Now, the next one we need is going to be in quadrant 2. So you can use the knowledge of reference angles and working backwards to help you with that. So what I mean by that is typically what we do is we do 180 minus the angle, and it gives us our reference angle of 30. So what we're going to do now is we're going to work backwards. We're going to take 180 and we're going to subtract the 30 degrees from it to get the angle. So 180 minus 30 degrees, that is 150 degrees. So my second solution is 150 degrees. Now when you plug these values back into the original equation, it should make the statement true. So depending on your calculator and what we're doing, you can always use your calculator to double check you. So what that would look like is if I make sure that I switch back to degrees because my angles are in degrees. Okay, this is a way we can check our answer. If I type in 2 sine of 30 degrees and I put equals 1, if it's true, it's going to tell me that it's a true statement. If I type in my other angle, 2 sine of 150 degrees equals 1, it should say true because of that. If I accidentally made a mistake and I said that maybe my answer was 210 or I got an answer of 210 and I say that it equals 1, it's going to tell me that it's false. So you do have that option. I don't want us to rely on that option, but again, you always have a way to check your answers. So right here, these two are my angles, and they both fall within 0 to 360, so we're good on that aspect. If this were something that was maybe only from 0 to pi, then 150 would be excluded. Or if maybe it was from pi over 2, not 0 to pi over 2, or pi over 2 to 3 pi over 2, then 30 would be excluded. Looking at example 2, we're going to solve 4 tan x equals -4 for all angles on the interval 0 to 2 pi. So now, because of our domain restriction, our answer will be in radians. So we have 4 tan x equals -4. To solve and isolate my trig function, I'm going to divide both sides by 4. So tan is equal to -1. What you need to know is that tangent is only negative in quadrants 2 and quadrants 4. So we need to think of those angles. Well, we are going to first relate it to quadrant 1. And so for the tangent trick, remember you're trying to do the square root of the bottom or rad of the bottom divided by rad of the top. If I put down my ring finger, for tangent, rad of the bottom is 1 over rad of the top is rad 3. So I get 1 over rad 3. That does not simplify to -1 or 1, so therefore it's not my answer. If I put down my middle finger, I get rad 2 over rad 2. Rad 2 over rad 2 simplifies to 1. That allows me to identify my reference angle. My reference angle is pi over 4. So if I'm looking for something that is in the second quadrant, I can use my reference angle to help me like we did in the previous problem. But this time, instead of using 180, we are going to use pi. And I am going to subtract pi over 4 from it. So if I think about it as a picture, okay, what we want is we want to find this angle right here. Well, I am going to take pi, which is right here, and I am going to subtract this piece right here, which is pi over 4, and it's going to tell me what that angle is. Well, in order to add fractions, they need a common denominator. So to get a common denominator to be 4, this is going to turn into 4 over 4 because 4 over 4 is 1. So when I subtract 4 pi minus pi, I get 3 pi over 4. And so that is my first angle, 3 pi over 4. Then if I'm thinking in the fourth quadrant, the fourth quadrant is over here. So if I'm trying to find this angle, then I need to use 2 pi and subtract that reference angle of pi over 4 from it. So 2 pi minus pi over 4. In order to subtract, we need a common denominator. So this is currently 2 over 1. So if I multiply the bottom by 4, I need to multiply the top by 4, which gives me 8 pi over 4. Minus 1 pi over 4, and that gives me 7 pi over 4. So that would be my second angle, 7 pi over 4. Again, I'm going to show you one more time that you can use the calculator to check your answer, and after example 2, I will not use the calculator again. So I am going to plug in 3 pi over 4 into my 4 tangent x equals -4. So I get 4 tangent. Instead of x, I'm going to type in 3 pi over 4. And I just realized that I did make a mistake, so I do need to fix that before I hit equals. Because I'm using radians, I need to make sure that I switch my calculator back into radian mode. There we go. Now that I did that, I can hit enter, and it says error, so let me double check. It might not work for radians, so let me try one more time, and then if it doesn't work, then that again shows us that the calculator is not always 100% reliable, so we need to make sure that we know the unit circle. Okay, so tangent of 3 pi over 4 is equal to -4. Again, I got the same error message, so this trick does not work for radians. So please make sure that when you're dealing with radians, you know how to find the values, because our calculator does not help. You could switch it over to degrees, but if you make that mistake during that process, you may think one of the answers is right when it's not, and it might just take you longer. So that trick doesn't work. I didn't even show that trick in class, so it's okay. Example number 3, solve the square root of 2 or rad 2 times cosecant of x plus 2 equals 4 for all values of x in radians. So what we see here is that it says for all values of x in radians. That's pretty important because it did not give us a domain restriction. What we're going to do here is we're going to take this square root of 2 times cosecant of x plus 2 equals 4, and we're going to solve it for, or we're going to isolate the trig function. So first, we're going to start by subtracting on both sides. When we subtract, we get rad 2 times cosecant x equals 2, because this and this cancel out, and 4 minus 2 is 2. Then I'm going to divide both sides by the square root of 2. When I divide both sides by the square root of 2, those make a 1 or cancel out. We get cosecant x is equal to 2 square roots of 2. 2 divided by the square root of 2. Now, before you start trying to mess with the fraction, we actually have not been working with cosecant when we do the unit circle. We focus on sine, cosine, and tangent. So what you need to know is cosecant goes with sine. And if we think back to our SOHCAHTOA days, all I need to do to go from secant or cosecant to sine is flip the fraction, and it becomes rad 2 over 2. Now, up above, it told us that our answer is in radians, so I need the two angle values that would give me rad 2 over 2 as an answer, and it's positive. So remember, it is positive in quadrants 1 and quadrant 2. So I need my two angles. I would get pi over 4 in quadrant 1 and 3 pi over 4 in quadrant 2. Now, because we have no domain restrictions, what I need you to understand, and I'm going to draw a picture, you do not need this picture, I'm just explaining, is that because there's no domain restrictions, here's pi over 4, what happens is there are things called coterminal angles. We talked about them back in February or January, that are angles in the same position. They're just different degree measurements because they go around the unit circle more than one time. So currently, this right here represents pi over 4. But if I did one full revolution around, that is more than my angle, okay? If I added 2 pi to it, so if I added pi over 4 plus we learned 8 pi over 4 was 2 pi. Then I see that I can add them, and I get, that's not 8 pi over 2, that's 8 pi over 4. And when I add them, I get 9 pi over 4. Well, 9 pi over 4 is a valid answer to this question. So we have to take into account any possible angles. Okay, if I wanted to do another full revolution around, then I could do another full revolution around and I would get a different angle. So how we account for this when we have no domain restriction is we're going to put plus 2 pi, and it's going to be times n, where n can be any number. It represents the number of revolutions around the circle, the number of times you go around the circle. So the purple n would be 1, whereas the green, if I fix it, let me fix it here. The green would just be a second one around, and then my blue would be a third time around, like that. It also works for negative angles. So if I went in the negative direction all the way back around and got there, n could be that as well. So anyways, the whole point of that is to show you that there's an infinite number of possibilities, and we don't want to have to write out all of those possibilities. So we represent it just by adding 2 pi n to the answer. Okay, moving on to the very last example. Solve secant squared x equals 4/3 for all values of x in degrees. So this one we are solving in degrees. Our answers will be in degrees. So we get secant squared x equals 4/3. So I noticed that my trig function is already isolated, but it is being squared. So therefore I can take the square root of both sides. I take the square root of both sides. When I take the square root of secant squared, I just get secant x. When I take the square root of 4/3, what I need you to know is that you can take the square root of 4 and you can take the square root of 3 individually. So the square root of 4 is 2. The square root of 3 is rad 3 because it doesn't simplify. But the one thing we're missing, and anytime you're solving an equation that involves taking the square root, you have to remember plus or minus. So now that we have that, we do not know secant. That's not one we know secant, but we have not been focusing on secant with the unit circle. So all we're going to do is switch this into something we do know, which is cosine. Cosine is the opposite of secant, meaning all I'm going to do is flip that fraction and get rad 3/2. Now I want every possibility when cosine of an angle gives me positive or negative rad 3/2. So when it's giving positive rad 3/2, that would be in quadrant 1 and in quadrant 4. In quadrant 1, I get, let's see, we're doing in degrees, so that would be 30 degrees. If I use my reference angle, in the second quadrant, 180 minus 30 is 150. In the third quadrant, I would actually add 180 and 30 and get 210. And in the fourth quadrant, I would subtract 30 from 360 and get 330. Now, there was no domain restrictions, so the same thing would apply where we add, but this time we're adding 360 in to each of these. Okay, this one, it seems a little bit tedious So I am going to show you how this actually would be written because, again, we're not going to list all 4 of those and we might not see that answer choice. As a picture, I'm going to show you. You do not need to draw this, you're just paying attention. So what we have here is we have this angle right here, this angle right here, this angle, and this angle. So what we have currently is that we're just focusing on one angle and we're just going around and around and around. But if you notice, if I go from, I'm going to erase this one and this one. If I go from here to here, that's actually 180 degrees. If we think about it, this is 30 degrees. We said this was 210 degrees. 30 plus 180 gives me 210. If I add 180 again, it takes me back here. If I add 180 again, and again, it just keeps going around. So anytime you have angles that are in opposite quadrants, the diagonal quadrants typically works for tangent, but in this case it works here. What we can do instead is that we can write the answer as 30 degrees plus 180 degrees in. What that does is it takes care of the 30 degree angle and the 210 angle. And so to take care of the other angle or angles, I'm going to do 150 plus 180 degrees in, and that's going to take care of this angle and this angle right here. So if you need a better understanding of this, please make sure you ask in class. But again, I tried to color coordinate them so you can see, but this down here would be the final answer that we are looking for this problem. So if you have any questions over anything that we did here, please make sure you ask in class. Make sure you attempt the practice and ask any questions because we're going to keep moving on and we're going to add more complex topics with the solving equations. So if you don't have an understanding of it now, it's only going to hurt us in the future. So write down any questions, ask in class, and I will see you in class.